we're going to find what we need to run inside this directory, UKACM School. So we click there, and then we have the various tutorials that we're going to run today. So you click in the mixed linear elastic, and you will find there a param file that has to do with running analysis. But what we are interested in is incompressible elasticity.ipynb. So we click that again, and we are going to find ourselves in a series of cells of Jupyter. Andrei explained what Jupyter is before. Is an environment that allows us to have an interactive experience or work with a developed code, but also we are able to write text that is going to help us understand what we're going to do later on. You can see many cells here. Each one, they are divided in order to do a particular task or set of tasks grouped. And as Andrei said earlier, whenever we want to update something or run something, we have to first run the previous ones usually. And then, so if I want to run a cell that is later on, I cannot just run this. I have to run the previous cells at first. So what Richard actually has prepared here for us is a brief description of again of the standard formulation for linear elasticity and what is the mixed formulation for linear elasticity. And here you can see the Lamé decomposition for stress that we take into account the relationship again of pressure and the divergence of the displacements or otherwise the trace of the gradient. And here are the set of equations in the in the continuous setting. And you can see here how more or less the discretized system of equation looks like in the general case, where B could be 0, could be non-zero, depending on the choice of lambda, or rather Young's modulus and Poisson ratio. You can go and later on read if you want. Again, it's a repetition of what it was presented this morning on how to pick the orders of approximation for the case of Taylor-Hood element, where the displacement variable and the pressure variable are both sought in H1 space, and the Crozier-Ravier that is H1 for displacement and L2 for pressures. And what we're going to run today is the example that I showed. It's the Cook's membrane. There is no figure here, but I can just remind you. This is a 2D problem where there is like kind of a cantilever. It's fully fixed on one side. It has these dimensions on the sides. A force is applied at the moment, at least, that is equal to 100. And we want to find, to recover the displacements at this point, at the very tip of this. And let's go now through the cells in order to see how to run this. So this cell, you don't really need to understand this cell. We need to run this in order to be able to set the paths that we are going to need in order to run our problems. So you can either click on this cell and run and press run, or click on the cell and then shift and enter. So I can do that instead. And then this cell involves the generation of the mesh. So here Richard has has created the mesh by using Gmesh, which is an open source mesh generator. So here are things that have to do with the boundary conditions and the material law. Here it's about the fully fixed side. This is about the force that is applied. Here is the material law. But then this is the geometry here for the Cook membrane that you can play with. So as I said earlier, we have these points that we know the coordinates 48 and 60 and 44 are the key numbers for the coordinates. So yes, and this part is about assigning the kind of boundary condition to the physical edge of these boundaries. And also there are other functions, we can look at them into more detail in a bit, that have to do with post-processing, parsing the log files, because when we produce results, we are going to have a generation of outputs in a text format, and we need to parse those outputs in order to post-process the results. And also, this is the key function that is used to run analysis here. So the main things I wanted to discuss here is about the field evaluator here, which you can see these are the coordinates of the tip. Again, this is 48 and 60. And this is used in order to recover the displacements at that particular point. So you could trace other points if you like when you will run later on the analysis. Also, you can see that we need to define the Poisson's ratio and the Young's modulus. So these are the parameters that we need to change in order to change them. So if I search for where they are set, is at a different cell that essentially we are going to play with in order to change the outputs later on. So let me not go into more detail for this cell, and we can run this cell, and we can go back later on as you run analysis. And again, as Andrei said, when it's not an asterisk, it means that it has run. So this cell is done. And then, as I said earlier, this is the cell where we can define the force. This is force per unit length. So it's 6.25 at the moment. The unit length is 16. Sorry, the length of this edge is 16. And therefore, 16 times 6.25 is 100. You can play with that as well later on. And there is no force on the horizontal direction. Young's modulus, Poisson ratio. And yeah, potentially we can play also with order. So at the moment, the default order that we use for the analysis, this order refers only to the order of the displacement that is chosen and the default moment. Please, I would like to ask you not to change this number at all, because otherwise we might have issues with the resources because we don't have much. So we don't want to overflow the resources we have. So we can run this as well. This is just reading the parameters. This is nothing more. And based on them, we're generating a config and the mesh, a configuration file and the mesh that is used, that is reading the parameters that we have set in the previous two cells. And here you can see how this mesh looks like. We can play also with the mesh size. Element size, yes. So here you can see the element size. So you could see there, let's say if I put it to 2, and I run this again, you can see a coarser mesh. So this is more about looking into the geometry of the and the mesh refinement.
Sorry, Ignatius, could you just show that this is animated view that you can zoom in?
Yes,
you can
yes.
rotate
So
it,
we can rotate it, yeah, because it's 2D. But yes,
but you can zoom in if you make a really fine mesh in this content.
Yes, yes, we can see the mesh. Yeah, we can play with this. For instance, just put, let's say 0.1. I don't know if that is fine enough. Yeah, it takes a while. And then if we zoom in, I don't know why I cannot zoom in. Oops. Yeah, so this is quite fine mesh. Yeah, I wouldn't dare to run this, so I will put it back with one core. I wouldn't dare. Put back to 1, let's say, and then. Yep, and then this is just one run based on the incompressible formulation for the mixed. So whenever you see this incompressible means mixed, this is showing the path to the executable that is needed in order to run this with mixed. And this flag is the flag where you can switch between Taylor-Hood, that is H1H1, or Crozier-Ravier, that is H1L2. And when it's 1, it means that Crozier-Ravier is switched on, because it means that the pressure is discontinuous is in L2. And as I said, this is we can change them also later on, and also at this point, we override always whenever we want these variables. So this is for displacement 2. And if I run this analysis runs pretty fast, and we can post-process the results. And we can see how the displacements look like in the vertical direction, or how the pressures look like. And you can see that the pressures are discontinuous. But let's just play with this. This is just one run, so we can just try this. And by putting 0 again, this is a flag about not setting a discontinuous pressure. So we're going to run Taylor-Hood. It's pretty fast because the mesh is quite fine, quite coarse. So we can post-process again by replaying this cell. The displacement field seems fairly similar to the previous one, but let's see now the pressure. And you can see that the pressure now is changing smoothly, because we have chosen to seek for the solution of pressures in H1 that is a smoother space. Okay, and this is like the more, let's say, interesting part. This is a script that runs over a loop of element sizes, of mesh sizes, where these are, let's say, an eighth, a fourth, half equal to, and then larger than this parameter here that you can find above as well. How much is, if you just search for this. Sorry. Yes. So this is now 16 at the moment, but you can play with that later on if you like, to make a different, let's say, spectrum of comparisons. Or you can increase this this list, like, I don't know, like this. Something small, let's say 1, like that. So makes it larger. And the main thing here is that for each case, there is a different mesh generated, and for each mesh, the same problem is run for 3 cases. One that is for mixed formulation, and you see the pressure is set to the discontinuous pressure is set to 1. That means that is in L2. So this is the first case is Crozier-Ravia. The second case, again, we use incompressible, like mixed formulation, but now the pressures are in H1, so Taylor-Hood. And finally, we have the standard formulation. So this is like the path for this executable that is changing, where again, the displacements are only the unknown, and they are always in H1 second order. So we can run this as well. This will take a while because we are running, now it's, in my case, 1, 2, 3, 4, 5, 6, 7 meshes times 3 cases, 21 analyses. The first analyses are quite, I'm not sure in which, okay, maybe.
It's looping over the element size list as opposed to element per side.
Okay, so
Yeah.
okay. Thank you, Richard. So if I put like,
yeah,
like something like this, okay. Okay, so then it will be anyhow 1, 2, 3, 4, 5, 6, 6 cases. So 3 times 6, 18. But we can check if it ran from the asterisk. So for me, oh, it just finished. So then this is producing a log file. You can see this log file here, and you can see other files that are generated in mixed linear elastic directory. And the thing is that here we want to plot the results. So we're running this plotting. Okay. Not sure what happened in this case. Let me see.
Probably it's because you changed the number of
you can
elements.
rerun it, and yeah.
Let me just.
Okay. But they run just this this definition of the element size.
Mm-hmm. Yeah.
No, but you run everything. Okay.
Yeah, but.
Okay.
I think it is because of the different rank sizes between the RM per side and RM.
Yes.
Yeah.
But now I think it's fine.
When I ran it, it was, this one was missing. And then I went, but this was here. So I had to rerun this to read this. And yeah, so whenever you want to change something, you have to go always back to wherever the variable is changing, and then rerun the target cell. This is going to take a while. So, okay, no, I think this will take a while. So for the interest of time, sorry for that.
Maybe Ignacio, while it's computing, you could suggest what would be the tasks for everyone.
So some of the task would be, you could change. Maybe I can also put the keywords to search for them in the chat. So one would be changing the Young's modulus and Poisson ratio, and see how the results are changing potentially. So I will put them here. You can also try and see, because now the Poisson ratio is set to 4.999 instead of 5, because we know that for the standard formulation, this will blow up. You can try to see how it blows up, what would be the one case, or you could change it. There is this possibility that you could change it only for the analysis that are running for the Schur complement, for the incompressible mixed formulation, and you can just set it only for these two analyses equal to 5. So you have to change it and put it here. That would be one case, just for this particular one. Another thing you could do is maybe extend this list as I did before, but I didn't finish this, and see how, for finer mesh, it changes. So it would be change the element list. Other things, you could change the force here. These two, actually, you can play with them if you like. And see how the results are changing. I would start with that. Essentially with Young modulus and Poisson ratio, and then maybe with the element size as well. And let's see what results this produces. Maybe you have already seen, you have already run that. Yeah, you can see how the results for the vertical displacements at this point converge when increasing the mesh size. So we can see that they all converge towards one value, but we can see that there is, I mean, if we just take into account only these results, from, let's say, more continuous to less continuous results, we are converging from below, apparently. I think Łukasz wants to say something. Yeah, I cannot hear you, Łukasz, for some reason.
Lucas is not connected properly to the audio.
Ah, I see. I see him. He wants to say something.
Lucas, we cannot hear you. You're not connected. Can you hear us?
Oh, he cannot hear us.
No.
I don't know. Maybe
Okay,
he is another meeting.
I will let him know.
Maybe he's in another meeting.
Maybe.
Okay. And I don't know if you want to go into more investigations, you can always change geometry and like here, and what else? But be careful that whenever you change geometry, these coordinates have to follow that geometry. So yeah. Or another task would be to keep the geometry the same and see at different points how results are changing. So you can keep the geometry the same, maybe even keep the material the same, and just roam around your domain and see whether you can find maybe a point where this difference is larger, potentially. So if I put, for instance, I don't know, let's say 12 and 40, I will get different results because that would be a different point, and you can see how the results are different. Are there any questions?